A warm welcome all my dear students in today's lecture. The topic of today's lecture is slope deflection equation. In previous lecture we have seen how to solve indeterminate beams by using three moment theorem. How to apply the three moment theorem for continuous beam we have seen in our previous lecture. Okay? As I have told you in the beginning, that is, in this entire structural analysis 2, we are going to analyze indeterminate structures like beam, truss or frame by using different methods. Okay? So our today's method is slope deflection equation or slope deflection method. Okay? So first we'll see what are the assumptions in this method, and then we'll proceed with the stepwise procedure to find out the solution for the indeterminate structure by using this method. Okay? So what are the assumptions? Let us start. Okay? So first assumption is, see the figure which I have drawn here, figure number 1. Okay? So first assumption is all the joints are rigid. All the joints are rigid. The angle between any two members in a joint does not change even after deformation or even after action of loading. Okay? See here, this is the frame where this angle is given, which is theta. And here, after the deformation also, the angle between these two members remains same. Though the members are deformed, the angle remains same. Okay? So this is our assumption number 1. All the joints are rigid and the angle between any two members in a joint does not change even after action of loading. Okay? So this is first. Then second is distortion due to axial deformation. Distortion due to axial deformation. Okay? So what is distortion due to axial deformation? See here in figure number 2, this is the frame. Frame is given here, and see there is a displacement of point B to B dash. Similarly, the displacement of point C to C dash. Now the deflection, horizontal displacement of B to B dash is delta. So at the same time, this C to C dash is also delta. Hence there is no distortion due to axial deformation. So the delta value remains same. Okay? So axial deformation in such frames or in this method is neglected. Okay? This is our assumption number 2. Okay? We have to follow these two assumptions while solving the examples by using slope deflection method. Okay, now what are the sign conventions which you are going to be used in the method? So what are the sign conventions? Okay, so we have to fix up the sign conventions for the moment and for the slope. Okay, so first, what is the sign convention for movement? If the movement is clockwise movement, then we will consider it as a positive. And if there is anti-clockwise movement, we will consider it as a negative. Okay? This is about the sign conventions for movement. Now we will see how to fix up the, how to take the sign conventions for the settlement and slope. Okay? So first of all, we will see what is the sign conventions for the settlement. Okay, so if the beam support gets settled, now this is a continuous beam. Now here the B support is settled by an amount delta. Okay. Now whether the settlement is to be taken as positive or negative. Okay. So for that we will fix up the sign convention. See, if the right side support is below the left side support, then the settlement is considered to be positive. If right side support is below the left side support, then settlement is considered to be positive. On contrary, if the right side support is above the left side support, then we have to consider that settlement as a negative. Okay. Now see how will we apply here. Now if you consider the AB span, now AB span, see the figure will be like this. This is A support position and this is B support position. Now right side support is B, which is below the A, means this delta is positive for AB span. Whereas if you consider the BC span, now C is above the B, whereas C is the right side support. Now see, right side support is above the left side support. It means the settlement is negative. Means a same settlement, but we will consider this settlement as a positive for AB span and negative for BC span. This is how you have to take the sign conventions when the settlement is there. When there is settlement. Okay. For movement, clockwise movement positive and anti-clockwise movement negative. Now what about the slope? What about the rotation? Okay. So clockwise rotation of a tangent to the elastic curve is a positive rotation and anti-clockwise rotation is a negative rotation. Okay. So if the rotation is clockwise, if the member's rotation is clockwise, then it is positive. If the member rotation is anti-clockwise, then it is negative. So see, how will you fix up the sign? We'll see the diagram. Okay, now this is the tangent and this is theta, tangent to this horizontal elastic curve. Now this angle of this rotation is, see, this is clockwise. This is clockwise. So this theta 1 should be positive. Then now this is theta 2. But see the sign of theta 2. We will start this from the original beam position and we will point the arrow towards the deflected position. So this is original position and we have started, and this is the deflected shape, final shape after the loading. Okay. So this theta 2, what is the sign of this theta 2? Is again anti-clockwise, not clockwise. So theta 2 will be minus. So theta 2 will be negative. Then next, what is theta 3? Again theta 3. Theta 3, see, this is also anti-clockwise. Theta 3 is minus. But what about the theta 4? What about the theta 4? So we will start with the original position to the final. Then again, see, the sign of this theta 4 is positive. So theta 1 and theta 4 is positive, whereas theta 1, so theta 2 and theta 3 is negative. Okay. So we will see how to proceed with this slope deflection method. Okay. So we will see the design procedure for the slope deflection method. So first of all, we will see for which type of structure this method is applicable. So which are the different structures which can be solved by using this method. So first is a continuous beam. We can analyze a continuous beam. We can draw a SFT-BMD for continuous beam. Second is we can analyze the frame with side sway. We can analyze frame without side sway. So what is side sway? With sway or without sway, what is with sway, what is without sway, we will see in detail in our next lecture. Okay, so today we will focus only on the beam. Okay, how to analyze a continuous beam by using this method. Okay, so in three movement theorem, we have considered each span of a beam as a simply separate span. Okay, so similarly here we will consider each span of a continuous beam as a fixed beam. We will consider each span of continuous beam. Now this is beam ABC. Suppose we have to analyze this ABC. So we will consider AB as a fixed beam and BC as a fixed beam. Means both the ends are fixed. Okay. Now when there is a fixed support, there is a support moment at fixed support. Okay. So definitely here support moment will be here also, here also, here also. Okay. So first step is to consider each span of a beam as a fixed beam. Okay. And find out this fixed end moment. This fixed end moment. This is called as, means support moment at fixed support is called as fixed end moment, and it is represented as, for this it will be represented as MFAB. This is A and this is B, and this will be represented as MFBA. Similarly for this MFBC, and for this MFC. Okay, so first step, consider each span separately as a fixed support, fixed beam. Fixed beam means the beam which is having both the ends fixed. And find out fixed end moment. So MFAB, MFBA, MFBC, MFC. Okay. Now find out this fixed end moment. So there are different formulas as like your formulas to find out the pre-bending moment. Now if the uniformly distributed load is there and you have to find out maximum bending moment, so formula is WL square divided by 8 for simply supported beam. So similarly there are some formulas to find out the fixed end moment for the different loading conditions. Okay. Now suppose a point load is there in between. This is A and this is B. Suppose the point load is there. Then fixed end moment MFAB is calculated as WAB square divided by L square. And for MFBA, this formula will be MA square B divided by L square. If the point load was there and suppose you have to calculate free bending moment, so formula was WAB divided by L. But for fixed bending moment, WAB square divided by L square, WA square B divided by L square. See, what is the difference between fixed bending moment and free bending moment? Free bending moment means we are considering each span as a simply supported span, and here we are considering each span as a fixed beam. We are going to consider each span supported by fixed support. Okay. So this is our step number 1. Okay. So likewise there are different formulas to find out the fixed end moment for different types of loading. So just now I have told you about the fixed point load. Suppose the UDL is there, then this formula will become MFAB. This will be equal to minus WL square divided by 12. This is also minus because this is anti-clockwise, and MF, see we are talking about now BC. C will be, this is clockwise, so WL square divided by 12. Okay, means if the UDL is there, WL square by 12 is the formula, and if the point load is there, then the formula will be WAB square divided by L square or WA square B divided by L square. Okay. Now clockwise movements are to be noted as a positive movements and anti-clockwise as a negative movement. Okay. Now after this, by noting the bending moments, end bending moments, support bending moment in actual beam, we are to calculate this MA, MB and MC. Okay, this is our aim. This is our final aim. We have to calculate support moment at each side. Okay. Now, as this A is hinged, so definitely this will become 0 and C will also become 0. But suppose this A is fixed. This is hinged and this is roller and this is hinged. So now this MA will not be 0. Okay. So in that case, what? So you have to calculate that MA. Okay. So ultimate aim is to find out the support moment, not this fixed end moments. Fixed end moments is considering each span separately as a fixed beam, but actual beam is not fixed. Here one support is fixed, one is roller and one is hinged. So you have to find out the moments in actual beam, that is MA, MB and MC. So for that, slope deflection equations are there. For that, slope deflections equations are there. Okay. Now these equations, see. Now this MA, MB and MC I will write differently in different forms, which we have already written in 3 moment theorem, that was different. Okay. So here I will write in different forms, means now right now this is MA, but here I will write this as a MAB. MAB. Here this moment MB I will write as a MBA. MB. Here I will write this as MBC and here it is MCB. Okay. Because we are going to consider each span separately, we are going to focus each span separately. So this is MAB, MBA, MBC, MC. Okay. Now see. Okay. See this MBA and MBC. One is clockwise, one is anti-clockwise. It is nothing but MB. Okay. So if you do the addition of MBA and MBC, it should be equal to 0. Because while analyzing the frame, we have seen that suppose this is the joint. And here it is MA. So here this MA will be in different direction. So this MA and this MA should be same and equal and opposite in direction. So same but opposite in direction. So if you do the addition plus MA minus MA, it should be 0. Similarly, the same joint is there. B joint is same. I have written here separately, but the moment if you consider MBA and MBC, if you do the addition of both, it should be equal to 0 because this MBA and MBC is the same value, is only one value, but with the 2 different signs. Okay. While analyzing the reactions, while calculating the reactions in 3 moment theorem also we have done same. We were taking only MB, but while we were taking MB for AB square, we were taking it as a clockwise direction. But while we are taking it for the BC span, we are taking it in the opposite direction, that is anti-clockwise. So if you do the addition, that is clockwise MB plus anti-clockwise MB, it should be 0 because there is no any external movement over here, that is internal force. And addition of internal forces at any joint should be equal to 0 or should be equal to external force if it is there. Okay? So this MB is the external reaction. If you do the addition, it should be equal to 0 because there is no external load. Okay. Now let us move further. So this is what the support moment MAB, MBA, MBC and MC. Now by using the slope deflection equations, or by using this method slope deflection equation, we have to set up the equations for MAB, MBA, MBC and MC. So these equations are derived. So I am not going to in detail about the derivations. I will write the equations for this MAB, MBA, MBC and MCB, and I will explain the term. Okay. So what is MAB? It should be equal to MFBA plus 2ER divided by L into bracket 2 theta A plus theta B minus 3 delta upon N. This is for MAB. And what about MBA? MBA will be MF. Here it is MFA. Then we are going to talk about AB. Definitely here it will be AB. Now MBA, it will be MFBA plus 2ER upon L square divided by theta A plus 2 theta B minus 3 delta upon N. Okay. Now see, this is the equation for MAB, equation for MBA. Similarly, you can draw it for MBC. You can draw it for MCB. Now for MBC, what will be the equation? MFBC plus 2EI divided by L square into bracket 2 theta B plus theta C minus 3 delta divided by N. Now when I am going to calculate or derive equation for MCB, what will be the equation? MCB is equal to MFCB plus 2EI divided by L square. Now L is the span of CB. Okay. Into bracket theta B plus 2 theta C minus 3 delta divided by N. Now delta, what is theta A? Theta A is the slope at A. What is theta B? Slope at B. What is delta? It's a settlement of support for that particular span. And I have given the sign convention for this theta also and this delta also. Okay, EI is the rigidity, Young's modulus and moment of inertia. MFBA, MFAB, it's a fixed end moment. Fixed end moment. And L is the span of that corresponding span length of that corresponding span. Okay. Now this is our step number 2. First step, consider each span separately, calculate fixed end moment. Second step, derive the slope deflection equations for your span. Now this is 2 span continuous beam. Your equations will be 4. AB, BA, BC and CB. MBC and MCB. Okay. Now see, I will write the equations for the other also. MBC is MBC plus 2ER divided by L square into bracket 2 theta B plus theta C minus 3 delta divided by L. Okay. Then MFCB plus 2EI divided by L square 2 theta C plus theta B minus 3 delta divided by L. Okay. Now what is next step after this? So first is you have to simplify these equations by putting the known values of these terms. So now MFB is known to you. Here value will be given in the example. Now what about theta A and theta B? See, theta is the slope. Theta is the slope, and the slope at fixed support is 0. Because in the starting of the structural analysis 2, we have seen degrees of freedom. So degrees of freedom for fixed support is 0. So there is no vertical displacement, there is no horizontal displacement, there is no rotation. Okay? So this theta value will be 0, means theta A will be 0. Now theta A कुठे कुठे असेल या पूर्ण इक्वेशन्स मध्ये ती व्हॅल्यू 0 येईल. Okay? Now what about rotation at B? There will be some value of theta at B. Similarly, there will be some value of theta at C. Okay, so this theta B and theta C are unknown values to us from these particular equations. Okay. Now, similarly, unknowns are MAB, MBA, MBC, and MCB. So, deriving these 4 equations is not just enough to calculate these values. Okay. So, you have to set up some additional equations also. And which are these additional equations? That is joint equilibrium equations. That is joint equilibrium equations. Now, as I have told you here, at joint B, this MBA and MBC, if you do the addition of MBA and MBC, it should be equal to 0 because there is no any external movement at B. MBA and MBC both are the internal movements, and if you do the addition, it should be equal to 0. So this is one joint equilibrium equation. So joint equilibrium equation is, for B support it is MBA plus MBC equal to 0. One more equation can be derived here or can be developed for this particular beam. That is, what about MC or what about MCB? MCB. See, MC is the movement at support C, whereas the support C is hinged and end support. I have told you in my previous lecture, if the end support is roller or hinged, then its movement will be equal to 0. It means that MCB is equal to 0. Is equal to 0. Now if you put the value of MBA, this entire equation, at the place of BC, if you put this entire equation, and this MCB is equal to 0, if you put this entire equation and if you equate the value to 0, you will get the unknown values of theta B and theta C. Already theta A is known to us. What about the settlement? I have given no settlement here, so the delta value will be 0 over here. Okay? So, but by these two equations are there and our unknowns are theta B and theta C. So, two unknowns, two equations can be solved. Okay? Once you got this value of theta B and theta C, you can substitute the values in these equations and you can calculate MAB, you can calculate MBA, you can calculate MBC, and you can calculate MCB. Once you calculate the support moment, you can draw the free bending moment diagram and you can superimpose the moments, that is support moment, on this free bending moment diagram to draw the resultant bending moment diagram for the given beam. Okay, so this is what the procedure for the analysis of indeterminate beam by using slope deflection method. In our next lecture, we will solve one numerical, one beam by using this method. Thank you.